Hi, I'm Karthik, and I'll be presenting PASTA, Proportional Amplitude Spectrum Training Augmentation for Syn-to-Real Domain Generalization, joint work with Prithvi, Vivek, and Judy at Georgia Tech. Synthetic data offers the promise of cheap and bountiful training data for vision models, where data can otherwise be expensive to collect. However, models trained on synthetic data significantly underperform on real-world data. Our goal is to bridge this gap and introduce a strategy to improve out-of-the-box synthetic to real or Syn-to-Real generalization performance of vision models. Prior works focusing on Syn-to-Real generalization address the problem through data augmentation, domain randomization, architectural changes, and various learning objectives. These methods tend to be useful in isolated settings specific to certain tasks, architectures, or domain shifts. We focus on creating a data augmentation strategy that works in any Syn-to-Real generalization setting in a plug-and-play fashion. We seek to discern the visual differences between synthetic and real images using the Fourier transform. Our primary focus is on amplitude, as it offers valuable insight into the photometric properties of an image, as established by previous research. Our approach, PASTA, is based on the insight that the amplitude spectra of synthetic images differ structurally from those of natural images. For the remainder of this presentation, we assume that the amplitude spectra are zero-centered, meaning the low-frequency components have been shifted to the center. For both the synthetic and real datasets, we take the amplitude of each image and discretize the spectra into low, medium, and high-frequency bands. We then compare the standard deviation of the values in each band between the synthetic and real datasets. Here, we assess the diversity of the amplitude bands in our synthetic dataset, GTA5, using the standard deviation of the values in the amplitude bands as a measure for diversity. When comparing the amplitude band statistics between GTA5 and the real-world datasets, we notice a distinct disparity between them. In the high-frequency band specifically, we see that GTA5 images are less diverse when compared to real-world images. This observation holds across multiple Syn-to-Real shifts and frequency band discretizations. Leveraging our prior observation, we create an augmentation strategy to perturb the amplitude of a synthetic image. First, we take the 2D FFT of an input image to obtain the amplitude and phase spectra. We then apply an element-wise multiplicative jitter to the amplitude to create a perturbed amplitude. This step is what we call PASTA, which we'll elaborate on soon. Finally, we combine the perturbed amplitude with the original phase and execute an inverse 2D FFT to transition back to the image domain. To address the diversity gap in high-frequency components between synthetic and real images, we perturb the high-frequency components of synthetic images more than the low ones. This can be seen in the epsilon matrix, where higher magnitude jitter values are shown by darker colors. Epsilon's values are determined by sampling from the sigma matrix, where each element in sigma specifies the standard deviation of the distribution for each element in the epsilon matrix at the same spatial position. Simply put, sigma determines the perturbation strength for each frequency. To construct the sigma matrix, we begin by adding a uniform constant for a base level of perturbation across the amplitude, controlled by the hyperparameter beta. We also introduce a frequency-dependent component, f-spatial, representing the distance from a value spatial position to the center of the matrix. F-spatial ranges from 0 at the center to 1 at the corners. As frequency rises, alpha controls the linear scaling of sigma values, while k allows for the exponential scaling of values. Both are crucial for perturbing high frequencies more than the low ones. On semantic segmentation from GTA5 to real datasets, PASTA outperforms state-of-the-art methods that use more complex architectures or more data than just the training set of GTA5. Those methods are represented by yellow bars. PASTA also outperforms state-of-the-art domain adaptation methods on object detection from Sim10K to cityscapes. Note that unlike the methods in red, PASTA has no access to real images during training, and yet it still beats methods with access to real images when evaluating on the same. Finally, PASTA results in improvements across backbones, initializations, and different tasks. In conclusion, PASTA is a simple, lightweight augmentation strategy that can fit into any vision pipeline. PASTA results in improvements regardless of the backbone or initialization. And PASTA works even when coupled with existing generalization methods. Be sure to check our poster out on Friday at 10:30 to 12:30 if you're interested in learning more. Thank you.